Welcome back. Today we're going to continue with our area under the curve discussion using integration and use it in order to find the volume of a solid. So for example, if we consider this curve f of y equals f of x, and we shade under the area underneath it between the function and the x-axis, and then bounded on the left by a and b, we can solve for the integral of that function with respect to x, and that will give us the area under this curve. All right, now if we took that area, this two-dimensional drawing here, and we rotated it around the x-axis, we could create a solid that looks like this. We could now find the volume of this solid by dividing it into an infinite number of infinitely skinny disks. And then by finding the volume of each one of these infinitely skinny disks, we could find the total volume of that solid. So that's how you extend area under a curve to find the volume of a three-dimensional shape. Okay, here's an animation on GeoGebra demonstrating what we were just talking about. So I've got this function here, 1/18 x squared, and here's my a value, which I just made 3, and my b value I made 9. Now, we know that from our earlier work with Riemann sums, we can divide this area, we can subdivide it into an infinite number of rectangles so that they fit the curve. And that's how we get the area beneath that curve. That's what integration does. Right now, as you watch over here on the right in this three-dimensional drawing, the way that we find what we're going to do now is we'll rotate this. So I'll make fewer rectangles now. Now, as I rotate this around the x-axis, it's going to create disks. And then I can find the area of each one, or the volume of each one of those disks, add those up, and get the volume of the solid. All right, so here's what our solid would end up looking like. So as we initially started here, there's our rectangles, and as we rotate those around, they sweep out these disks. Now, the more rectangles we create, the smoother this disk becomes. And now I can find the volume of that by adding up the volume of these individual disks. So as the more disks, the more accurate our calculation for the area under the curve, and the more accurate our volume. So this is called the disk method, because you're literally finding the volume of each one of these disks, and then finding the sum of all the disks, and that's the volume of your solid. So that's what we're going to talk about today. So to find the volume of one disk, let's say we're going to find the volume of the disk that is created by this rectangle right here. All right, so we have, to find the volume of that disk, we need to know the radius of the cylinder, that disk. All right, so that's going to be, the radius is going to be the same as the value of the function. So if we just call this f of x, this would be the value of the function at some particular x value, right? Then to get the height of the disk, so before we go any further, volume of a cylinder is pi r squared. That's the volume, that's the area of the circular part, times the height of the cylinder. Well, the height of our cylinder is dx. So as the heights get skinnier and skinnier, the more accurate this gets. So we would have pi r squared, but r squared will be represented by the value of the function. So pi, the value of the function for this particular x value, squared, that's the radius, times the height of the disk, its thickness. All right, and we can see as I make more of these disks, that height gets infinitely small, and eventually we get a very accurate approximation of the volume. All right, splendid. Now, our formula for finding the volume of a solid is, if you take a look here, we have a disk on the left, we have a disk on the right, and then we have a random disk in the middle, or somewhere between the two. Now, to find this volume, as I just explained, this value right here on the x equals a. The radius of this disk is whatever the function value is when x is equal to a. So we call that radius f of a. Okay? Just like if this was some x value, the radius of that disk would be the y value f of x. When I plug x into this equation, the y value would equal the radius. Okay? If this was b, then this distance is f of b. I plug b into that formula, and whatever I get for the y coordinate, that is the radius. So to find the area or the volume of a disk, we take the area of this circle, which would be pi, radius squared. Remember, this is just the radius. Pi radius squared, pi radius squared, and then that's the area of the circle, and then to get the volume, each one of these would get multiplied by its height. So down here, we get this is the volume of each disk. And we're finding the sum of all those volumes as the height of the disk, or the thickness of the disk, approaches 0. So we know a summation is the same as an integral from our work with Riemann sums. Think of pi as a constant, so I can pull that out. So to find the volume of a solid, you're simply finding the y-coordinate, squaring it, and finding the integral from the limit, or from the lower bound to the upper bound, and then multiplying that by pi. Extraordinary, isn't it? So our formula for finding the volume of a solid is pi times the integral from a to b of the function that generates our solid. Okay, now this is the function y equals f of x. So this is the same thing as me just writing f of x squared. That's the radius of each one of the disks times pi. All right, so we want to find the volume of a truncated cone here. It's like a cone with the top cut off. So here's our function, y equals x, which is just a diagonal line. So to find the volume, we're going to go pi times the integral from 1 to 4 of x. So now I'm sorry, this would be x squared. So now I integrate that, and I would get pi times the integral of x squared is x cubed over 3. And I'm going to evaluate that from 1 to 4. And then when I'm done, multiply that by pi. So I get 4 cubed over 3 minus 1 cubed over 3 times pi. So 64 over 3 minus 1 over 3 would be 63 over 3, which is 21. So my volume is 21 pi, and whatever units we're in, so I'm going to just say we're in centimeters, so I'd say cubic centimeters, and that's my volume. Okay, find the volume. Okay, let's continue. Find the volume of a solid formed by the equation y equals x squared. So x squared is making our radius. So my radius squared times pi is the area of the circle, and then I'm multiplying that by the height. Okay, so r squared, which in this case is x squared, and there was a little typo. This is 5, and this was a 4, so I scratched that out and made it a 5. And I take pi, x to the 4, dx, integrate, evaluate, and this would simplify to pi. 5 to the 5th over 5 would become 5 to the 4th minus 0, equaling 625 pi centimeters cubed as my volume for that solid. So the function that you are given, as it's rotated around the x-axis, this is actually the function that is the radius. So we have to square the radius and multiply it by pi in order to get the area of the circular base of each cylinder. And then we multiply that by the height to get the volume. So to set up our formula here from 0 to 5, our radius is the square root of 25 minus x squared. Quantity squared dx times pi. Now, conveniently, that square and square root undo each other, which turns this into 25 minus x squared dx. And now I integrate and evaluate. And there you have it, for a grand total of 250 over 3 pi centimeters cubed. Okay, our next equation is to take this area under the curve E sine 2x between 0 and 2, rotate that about the x-axis, creating the solid, and then calculating the volume using technology. Now, at first I'll show you a Desmos file that is set up exclusively to demonstrate revolving the solid about 360. And then also demonstrate how you could use Desmos, just plain Desmos, to just simply type in the integral. Okay, so there's quite a bit going on in this Desmos file. Right, what you are going to be concerned with is finding the equations, which are right here, the primary input functions. And I am going to enter there e to the sine x. Now, my second function is simply the y-axis. So that would be y equals 0. That's this function right here. So what we're looking at is this curve. And then we're going to take that curve and rotate it about the x-axis. So if you grab this dot here, you can change your perspective. And I'm going to now to rotate that to revolve it. I go down to 24 here and revolve that about the y-axis. And I get this shape. So if we change our perspective, just because this is so cool, and now we revolve that around our x-axis. And we want to calculate its volume. All right, our two bounds were between 0 and 2. So my boundaries are right here. So I will have x, the x1 is 0, and x2 is 2. Right? And you can see on the top, that is giving us, here is our volume. This is the surface area, this bottom formula. We're interested in the volume, which is our top one. And there you have it. There's your integral. Now, if I simply just typed in this integral, so in here, this would be from 0 to 2. This is e to the sine x, which is my radius, squared. And there's my integral to 3 significant figures, 30.2 centimeters cubed. So you can just type it in. I like this because you can see it, you can visualize it. Okay, splendid. All right, one arch of y equals sine x between 0 and pi. And it says to use the identity. So we'll do it first using Desmos, and then we'll do it algebraically. So on Desmos, I am going from 0 to pi. And my equation is y equals sine x. From 0, x2 is pi. And here are my revolutions as I rotate that around. Okay, I get this shape. Oh, excuse me, I think I made an error here. this is x1 is 0, and x2 was pi. Terribly sorry. All right, now to do this analytically, pi okay. Now, when we evaluate sine squared, that is the same as sine square x dx. And I'm reminded then to use this identity to integrate. So I can rewrite this as an equivalent integral which is far simpler to integrate. Okay, I can factor out, before I even start to integrate, I'm going to factor out the 1/2. Making it a constant, and therefore I can pull it out front. Okay, now we will evaluate this integral, and we will use u substitution to evaluate cosine 2x. So we will let u equal 2x du equals, divided by 2 is dx. All right, now we will substitute that into our integral. This is really a 1/2, which I could pull out front and pull out in front of my integral symbol. And now, with all due haste, we shall integrate so the integral of 1 is x minus the integral of cosine is sine. I will substitute my value of u and there is my integral. So altogether over here, I have 1/2 pi this would then be 1/2, which I could factor out. So why don't we do that? So I'd have another 1/2 out here, making it a 1/4. And inside I have x minus sine 2x. And I want to evaluate that from 0 to substituting in pi. This would become sine 2 pi. And at 2 pi, the sine value is 0. That is simply 0 minus, substitute 0 in for x, minus Now this would become sine 2 times 0, which is sine 0 this time. And the sine at 0 is the same as the sine at 2 pi, 0. So I end up with 1/4 pi. This is all a pi, so this is simply pi squared, units cubed. And if we work that out, we would get roughly 4.93 cubic units. And here it is, just simply plugged into Desmos. And we can use that to confirm our solution. All right, our final volume is to find the volume of a solid created by the equation y equals the square root of sine x. So sine x square root is my radius. So I shall have pi 0 to pi sine x dx quantity squared, which conveniently cancels out the square root, and I end up with sine x dx. And now we shall integrate. Okay, and our integral of sine x is negative cosine x. So we will evaluate negative cosine x, evaluated from 0 to pi, times pi. All right, cosine at pi is negative 1, and the cosine at 0 is positive 1. So we will have pi, substitute in okay, this is negative 1, which is now positive 1, minus. This is positive 1, so I got negative, negative 1, which would be plus 1. And I end up with 2 pi cubic units. All right, that will do it for today. It's been a pleasure working with you. Uncle Donnie, thank you very much for letting me stand in and work with these fine students of yours. Good day.